In example 1, we looked at the electric field intensity generated by a current being ramped in a solenoid. Here we are going to build on that example. In example 1, we had a solenoid and we ramped the current so that there was an increasing magnetic flux in the plus Z direction. To the right here is a cross section through the solenoid. So the solenoid is sitting here, and what we found was that the resulting electric field intensity was circles around the solenoid in the clockwise direction. For the parameters of example 1, the integral of E dot dl clockwise around the solenoid results in an electromotive force of 6 volts. Let's put a ring of material around the solenoid. The properties of this ring of material are such that if you placed a cut through here and measured the resistance from one end to the other, you would get a resistance of 6 ohms. Because of the ramping flux through the solenoid, Faraday's law tells us that the integral of E dot dl around the solenoid will equal 6 volts, even if that integral is through this new material that has a total resistance of 6 ohms. So the electric field intensity inside this resistor is 6 over 2 pi rho volts per meter. So the electric field intensity inside this resistor will cause a current to flow, and the current will be the same everywhere inside the resistor. Let's apply Faraday's law around this path that's inside the resistor. So the integral of E dot dl around this path will be the current flowing times the total resistance of our resistor, which is 6 ohms, and that's going to equal our electromotive force, 6 volts. So the current flowing in the resistor will be 1 amp. Let's model our ring as a series of distributed resistors. So here is such a model where I've used 6 1-ohm resistors in a ring. So we found that we have 1 amp flowing, so the voltage drop across each one of these resistors will be 1 volt. So if we start at this point and sum the voltage drops around this closed loop here, we will obtain 6 volts. So the sum of the voltage drops around this closed loop is 6 volts and not 0 as Kirchhoff's voltage law would tell us. Kirchhoff's voltage law is not a fundamental law, but Faraday's law is a fundamental law. When the electric field and voltages are being produced by a changing magnetic field, one has to use Faraday's law and not Kirchhoff's voltage law. Kirchhoff's voltage law is a special case of Faraday's law when there is no change in magnetic flux with respect to time, so that the right-hand side of Faraday's law is 0. In the next video, our third example, we're going to cut this resistor in half and remove half of it from the picture.